Greetings, and we are still doing the same examples on the shear force and bending moment diagram. And today we're going to carry on with one of the examples. Now, we're dealing here with a uniformly distributed load on a beam that is a cantilever beam. And we are given this loading of a UDL that is 10 kilonewtons per meters for a beam that has a length of 6 meters. And because it's a cantilever beam, it means it's fixed one side. A cantilever that is vertically determinate is only fixed one side. Now the question here is exactly to get first of all the reaction and also draw the shear force diagram and the bending moment diagram. Now, first and foremost, as we know, in this kind of situation, we need first of all to calculate the reaction. And here, because it is a cantilever beam, we only have one point where the beam is attached. We have only one support, but we know that every time we're dealing with a cantilever beam, we will always have two components of the reaction plus the resistance moment, which is a total moment at this point of attachment between the beam and the other part of the structure. That's the concept. Now, let's get the UDL, the resultant UDL. What is it going to be? You know that the resultant UDL will be the load per unit of length times the length, which in this case will be equal to 60 kilonewtons. And because we're dealing with a UDL, we remember that generally to draw a free body diagram and a shear force diagram and a bending moment diagram, when we have a UDL, it's always good to represent that UDL as a function of the length, representing it as a mathematical function. And from here, how did we get the 60 kilonewtons? We got the 60 kilonewtons by taking the load per unit of length times the length, which was 6 meters. Because the length is our variable, our independent variable that will give us a total, which is our independent variable. Mathematically, we can have something like this. This is the depending variable. This was the load per unit of length times the length, which can be considered as x, which is in meters. The meters and meters will cancel, and therefore our UDL mathematically will represent 10x. But if it's in terms of the length if we calculate in terms of the value of the length, it's 60. Mathematically, it's representing the load per unit of the length times the length, which is x in this case. Now we know the total UDL, which is 60, and the position of the total UDL will be at the center of the gravity, which is half of the length, and I will put 10x here just to remember that we're dealing with a mathematical representation of the total UDL. We have the mathematical representation when we take the total length. But if we want to use the length as an independent variable, we can represent it as a mathematical function. Now, having that, the second thing that we need to do now is to calculate the reaction. And how do we get the reaction? As we can see, it's a cantilever beam. We have RAV here, RAH, which obviously will be equal to 0 because there's no other horizontal component. And also we have the total moment, which is always known as the resistant moment that brings the beam in equilibrium. Look at the direction of the total resistant moment. It's opposed to the direction of the moment that the load will create. The load on the beam, which is a UDL, will have a tendency of creating a clockwise, an anti-clockwise moment. Now, because the maximum moment is the one that is balancing the moment due to the load, this moment will always be in the opposite direction. That's what we need to remember. Now, let's have our RA. RA, here the horizontal component is equal to 0, as we can see. Therefore, the vertical component will be equal to RA. Because we have vertical component, the best equation that will help us to get RA will be the sum of forces projected on Y equal to 0, because we only have vertical forces. The horizontal component of the force, which was this, was equal to 0, or is equal to 0. And then RA will be equal to the sum of forces projected on Y equal to 0. And how many forces we have on Y? We have the load of 60 kN downward plus RA, which is RAV, equal to 0. And consequently, we can see that RA is equal to 60 kilonewtons. Because we've now got our reaction, the remaining is just doing the calculation for the shear force diagram and the bending moment diagram. How do we proceed with this situation? We'll do the same as we've done it before. If this could be my point B, I can start from B and going toward A. It's fine. Or else I can start that side. But remember very well that this is a cantilever and the maximum moment will always be here. And that maximum moment helps to balance the moment that is created by the load on the whole length of the beam. It means at this point, A, that will have the bending maximum moment here. Now, the bending moment diagram will definitely show us that this point is the maximum bending moment. Now, let's start with the shear force. This is our zero line. We already know that our reaction A is from this equation. Now, let's start our shear force diagram. Shear force is left. Starting from this side, we can also start this side. It comes to the same, we will get the same result. At the left of B, as we can see, at the left of B, there's no load, and it will be 0. Now let's move to B right. What do we have at the right of B? I'm in this zone. I mean, I can even use C here, but it doesn't matter. I can keep it like this. At the right of B, I'm in this zone, but I haven't covered the whole zone. I'm still on the UDL zone. And whenever I'm on the UDL zone, it's advised to use the mathematical expression or the mathematical representation of the UDL. Now, at the right of B, it's here, wherever it could be, whatever it could be, but we're still in the zone of the distributed load. And therefore, because we are in that zone, and that zone is it's reflected by the load that is evenly distributed, which mathematically can be represented as such. Therefore, what are we going to have? At the left of B, we have minus 10 X, which is 60 newtons, 60 kilonewtons if we've covered the whole length. Now, because the length varies, we can see X varies from 0 to 6. Therefore, shear force at B right will be, for X equal to 0, will be 0. Shear force at B right for X equal to 1. It means we substitute all the values of X from 0 to 6 in the function that is representing the shear force at B right. For X equal to 1, this will be minus 10. For shear force at B right, X being equal to 2, this will be minus 20. Shear force at B right, X, for X equal to 3, this will give us minus 30. Shear force at B right, for X equal to 4, this will be minus 40. For X equal to 5, minus 50, coming from this function, and X equal to 6, minus 60. These are the values of the shear force at B, at the right of B, for which the length varies from 0 to 6, and that's what we've done. The length is our variable, and you can see it goes from 0 to 6. And we can see from 0 to 6, which is the total of the length. These are the values that are showing us how the shear force is changing from point B to the total length, which is situated at A. Then, if we are finished with shear force at B right, shear force at A left. A left, still in the same zone, means we'll get the same function which will reproduce the same value. We'll keep it like this. Now we go to the right of A. At the right of A, we are now outside. After covering the whole length of our beam, this implies that now we have the total load of the UDL, which is 60. Because it's going downward, it will be minus 60. If we do the algebraic sum, as we said, it's minus 60. We're not going to use 10x anymore because we've covered the whole length on which the variable, the independent variable, is covered from 0 to 6. Here we are at A left. We consider now the whole beam covered by the UDL. We consider the virtual force, which is the resultant UDL. And obviously, when we are here, as you can see, we have two forces, 60 kilonewtons, and the 60 kilonewtons as reaction. It will be 60 plus 60. 60 being the RA, and 60 being the resultant UDL. And this will be equal to 0. And let's plot all these points. If we plot all these points on our shear force diagram, you will see that at B left we are at 0. This is done. At B right, that's where we have all these points. And we can plot all these points wherever we want. We can divide this length in 6 divisions because we have 6 points here. And these 6 points, as you can see, they are represented by a function in which x is a variable, an independent variable, and the value of the shear force at the right is representing the dependent variable. Then we'll have something like this. The equation that is represented by something like this. Now for the values of 0, x will be equal to 0. For the value of 1, it will be minus 10. And then minus 20, minus 30, minus 40, minus 50, and obviously minus 60. And this point will be aligned because if we look at this function, if we need to plot this graph mathematically, this graph will be mathematically, if we plot this, it will be something like this. This being our y, and this x, it will be a graph that will start from 0, because for x equal to 0, it will be 0, and all the negative values, all the values that we have will be all negative for x. And that's what we have, a straight line that will be like this. And this is our shear force, and the sign of the shear force is negative. Negative because all the values are below the 0 line. We're done with the shear force. Let's quickly do the bending moment diagram. Now from this shear force, as we can see, the section of the beam that can be subjected to the high shear force is this one. It means it's this point. That way the cutting effect of the forces on the beam will be more intense and more significant. This cross section is the one that is likely to be sheared off during the time this beam is subjected by this kind of loading. Now, bending moment. Let's draw the bending moment diagram. This one should be straightforward. Now, how do we proceed? Bending moment, we have a choice as well. We can proceed from B to A, or we can, that's the best way to go because the support is here, and it's better to go from that side to this side. Now, bending moment at B. At B, we have just the point, and there is nothing acting on B as a support. It will be 0. Bending moment, we can take a point here if we want to. There's nothing will change, but it will help us to get more accurately the diagram. But it's not something that should be done. Now let's take straight the bending moment at A. What is it gonna be? As you can see, A is still on the length of the beam. Now the equation will be this load, because this is the load that will create a moment. It will be, in this case, we can use 10x. And what is the distance? This is L over 2. We can consider it as x over 2 because we're still on the length of the beam. Therefore, the moment will be the load times the moment arm. The load times the moment arm. What kind of moment that will generate this kind of load? It will be an anti-clockwise moment. It means 10x as the load times the moment arm, which is x over 2. And this will give us minus 10x squared over 2, which is 5 minus 5 squared. A quadratic equation. It means when we are at A, x is equal to 6 when we are at A. Now x varies. We know that x varies from 0 to 6. Therefore, because we have these values, the bending moment at A should also be expressed in terms of the values that are in this interval where the load is distributed from 0 to 6. For x equal to 1, the bending moment at A, having this mathematical function, will be minus 5, 1 squared, which is minus 5. That is for x equal to 1. Okay, for x equal to 0, obviously the bending moment is for x equal to 0, bending moment will be 0. That's obviously. Now, for x equal to 2, this bending moment at A will be minus 5 times this will be minus 20. X equal to 3, the bending moment at A will take the value of minus 45. X equal to 4, it will be minus 5. It will be minus 80. X equal to 5, It will be minus 5, then 5 squared, which is 1 minus 25. Obviously, x equal to 6, it will be minus 180. These are the values of the bending moment from B to A, while A is our pivot. We know that the equation will give us this, for the total moment, and because this is an equation, x being a variable, an independent variable, which is the length that varies from 0 to 6, we'll have to plot all these values of x from 0 to 6 in order for us to read or to have a picture of how the bending moment is changing in this case. We can plot all these values by plotting these values. Because this is a quadratic equation, it will give us definitely a graph that is a curve, that should be curved. It can't be linear. Like in the previous case, this was a linear graph, but this one is a quadratic graph. It will give us something like this, to a point that this is where we get this value of 1 minus 180. Because we'll have other values like minus 5, minus 20, minus 45, minus 80, minus 125, and then 180. Then once we plot this point, we should be able to get a bending moment. And here, because this is a zero line, we decided to put the negative values below the zero line as per normal, and this will be negative. And this is all for this example. We have a UDL, the cantilever being statically determined. Let's see another example.